7:30 p.m. And if you want to go with us, there will be a crowd leaving at 7:10 from the hotel to the restaurant. Quito, please.
All right, thank you, José, for the introduction. And today I'll be talking about nonlinear spectroscopy in general, and especially applications to strongly correlated systems, and in particular, unique signatures of electronic nematic spin liquids. So let me start by acknowledging our collaborators in this project, Ihua Qiang, a PhD student from Iowa State, Thais Trevisan from UC Berkeley, who is also attending the workshop, York Shimalian from KIT, and Peter Orff, my supervisor at Iowa State, who recently moved to Saarland University. Okay, but in the spirit of this workshop, okay, it's not. The thing froze. Okay, it's back now. All right, so in the spirit of this workshop, let me start by going back to 2005. So 2005 was my last year of high school, actually, but it was also the World Year of Physics to celebrate the 100 years of the works by Albert Einstein. And University of Campinas had several one-day events to celebrate all this amazing work by Einstein. And I became aware of this first one in April, about 100 years of relativity. And just to give some context, I grew up in this town, Valinhos, which is just 26 minutes away by car, 1 hour by bus, to Unicamp. So I decided one day just to skip school and go to attend this workshop. The workshop was a lot of fun, but it was there that I also found out about this first school of advanced physics for high school students. So that sounded extremely cool. So I registered for that. And then in July 2005, I actually attended this advanced school. And by now, you probably figure out that Eduardo Miranda was actually the organizer of this school. And I keep a bunch of souvenirs from that particular week. It was extremely fun. Unfortunately, I don't have photos, at least I don't have the photos with Eduardo from that particular week. And I also keep this notebook that they gave to us to take notes. And I was revisiting these notes last week, and then I found Eduardo's lecture, actually. The collective behavior of matter, an introduction to superconductivity and magnetism. And I remember that this was extremely exciting at that particular day. I kept that in mind over the years. So he started with an introduction to gas, liquid phases, all the way to magnetism, superconductivity. And what was particularly controversial was this statement about the spin of the electron as an intrinsic property, and h divided by 2 pi, where h is Planck's constant. And Eduardo just told us that this comes from Dirac's equation for relativistic quantum mechanics. So as a high school student, this was very, very interesting, and I was definitely curious to learn more about all of this. And I started my undergrad at Unicamp in 2006, and I kept all of that information more or less in mind. Then in 2008, I went to talk to Eduardo, and he basically wrote down our first research project together about disordered spin systems. And then after that, in 2010, I started my PhD with Eduardo, also in this field of strongly disordered systems. Something that I would like to mention that was mentioned several times throughout the week is the quantum many-body course that we had the opportunity to take in Campinas. Many people from this audience actually took this course. I took it in 2011. It's almost a mandatory course for condensed matter physicists in Campinas who want to have a very nice understanding of our field. I still keep the copy of Eduardo's notes about this course, and I often consult these notes. So here is the first page, basically, where he defines the many-body problem and the basic tools, Green's functions, RG, mean field, all the familiar tools. What are the objectives, a microscopic description, linear responses, effective theories, and all the concepts like symmetry breaking, ergodicity breaking, universality classes, and all these things that we are actually addressing during this entire week. So these notes are a very important place to learn about all this amazing field. So this is the first photo that I actually have with Eduardo. This is in 2016 during my PhD defense. So I defended my PhD in 2016, and since then, for sure, Eduardo remains as a constant source of knowledge, of guidance, throughout all these years. And I would like to emphasize something that he showed me when I was still in undergrad, and he showed me this cartoon that he has in his office. Never, ever give up. And every time that we had a problem that we couldn't solve for a week, he would just point to the cartoons. Don't give up. And this was a very important message regarding projects in physics and life in general. So I'd like to thank Eduardo for helping me in this journey through the years. But obviously nowadays, the only real way to know a person is by maybe asking ChatGPT. What does ChatGPT know about Eduardo that none of us actually know? So I had to go there and type Eduardo Miranda Unicamp to actually learn who Eduardo Miranda is. Okay, so this was the answer that I got. He's a well-known professor, researcher in Campinas. Okay, this we know. He holds a PhD from University of London. Well, this is new, I mean, but okay. Pierce is British, so maybe there is a bit of confusion here. And he has made significant contributions in nonlinear dynamics, well, chaos theory, and complex systems. Okay, complex systems. Dr. Miranda is associated with the Institute of Physics Lab Vatagen, very good, we know that. He has been involved in research, intersection of physics, music, and artificial intelligence. Okay, it's coming, no spoiler, no spoiler. I didn't know, I had to find out. His work focuses on development of computer systems that can generate music and interact with human properties, well, human performance in real time. Wow, very cool. In addition to his research, Eduardo is also a composer and has performed his music at various international venues. So maybe he has a dual life, I don't know. He has published numerous papers and books on the topics of music, artificial intelligence, and complex systems. So I was thinking for a minute or two, how can this be? Either Eduardo has a dual life or something here is very off. So I went to Google, and then I found out that there is another Eduardo Miranda, who is also turning 60 years old this year. So it's a Brazilian composer. He stays in the UK most of the time, and that is the origin of all this confusion. That's very good. Okay. All right, so ChatGPT doesn't know something that we actually know, that not all Eduardo Mirandas turning 60 this year are the same. There are two different Eduardo Mirandas. Okay, with that, I would like to conclude this part of the introduction for the talk, and I would like to congratulate Eduardo once again for his 60th birthday this year, actually in October, that we are celebrating now. So thanks, Eduardo, once again. All right, with that, I will go to the physics part of the talk. And if you recall my title, I'm going to be talking about nonlinear spectroscopy. So why do we need nonlinear spectroscopy? So let's look back at the linear response regime. And again, for the linear response, we have the many-body course and the lecture notes. So the idea is that we hit a sample, let's say with an electric field at time 0, and then we perform a measurement at a later time t1, let's say. Here I'm showing a measurement of current. It's often convenient to look in frequency space, and it's a very successful technique for sure. But in today's talk, I want to explicitly show some limitations present in linear response. Okay, for that, let's say that we have two distinct peaks in frequency domain. Here I'm showing the two peaks. And we can ask, what are these peaks from? Are these two independent or interacting excitations? So two possible scenarios are either this, in which you have two non-interacting two-level systems, let's say. And another possibility is this one, in which you have a single three-level system. Probably these levels can have some sort of interaction that even splits the levels. So this we cannot know by looking at linear response alone. And it's particularly bad, especially in correlated systems, when we have a bunch of excitations, and these excitations become broad, because these peaks start to overlap, and then we get very limited information. So that's the motivation to look basically at nonlinear spectroscopy. So now we don't have only one pulse and a measurement, but instead we have a collection of pulses that are separated by arbitrary times. So here I'm showing two electric pulses at time 0 and time t1. So the first separation is t1. And the second independent time is t2. And then after that, we measure the current at t1 plus t2. So as usual, it's much easier to analyze what's happening in frequency domain. So we now have two independent frequencies that I'm calling omega 1 and omega 2. And now you see that the spectrum becomes decongested. So we have the bandwidth of excitations in one direction and the lifetimes in the perpendicular direction. And we can actually extract some information about these excitations, information that is encoded in the peak positions, so where these peaks appear. So what are the amplitudes of the peaks? How big are these peaks? The relative phases and how the line shapes look like. Here I'm showing more or less Lorentzian form. And this field of nonlinear spectroscopy has been important over the years. And I will just tell you what it can tell in terms of quantum materials. So it can provide information about electronic symmetry. So some higher order responses are greatly enhanced if you break some symmetries, for example, inversion symmetry. So it can also provide information about topology and the quantum geometry of the Bloch wave functions, as Thais told us earlier in this week. And I'll be focusing particularly in these two topics: the nature of excitations, their lifetimes, and their couplings, as well as the quantum coherences of the many-body quantum state. So I'll be devoting most attention to these two topics. And I would like to just briefly mention, we had some talks on Monday about Kitaev models. We have a recent work where we show that with nonlinear spectroscopy in the terahertz regime, with two magnetic pulses, we can disentangle the Z2 gauge fluxes and the Majorana fermion excitations. But I will not be talking, this is not the work that I'll be talking about today. So for today's talk, I'll be interested in separating a glass phase from a liquid phase. So let me define what I mean by that. So the motivation comes from a newly proposed electronic nematic liquid for this compound barium nickel 2 arsenic 2. So Raman measures above the transition from tetragonal to triclinic show some splitting of these peaks that we would expect to be related by symmetry, and therefore only one peak would appear as shown here at higher temperatures. And in this region, for this particular temperatures around 140 Kelvin, there is no magnetic order. So the splitting of this peak is probably, presumably, coming from orbital nematic fluctuations. So we define this orbital nematic order parameter, which measures the relative occupation of the dxz and dyz orbitals that are related by symmetry in the C4 case. And then we couple it to phonons. So this is the coupling in real space. As you can see, it factors out. We can solve it site by site. At least this term, we can solve it site by site. And with these ingredients, this work, which is an experimental work, in collaboration with the theory group of York Schmalian, they also proposed a theory model that can, in principle, capture some of this physics shown here. In today's talk, I want to revisit this model and ask the following question. Can we clearly distinguish this liquid phase, the proposal of a liquid phase here, from possibly a glass phase? And I will define what I mean by liquid and glass phase in a moment. So the model that is proposed is a simplified model for the nematic liquid. Basically, we start with a Hamiltonian that is just two Einstein modes that are decoupled in the x and y direction. And these Einstein modes can now interact via this parameter lambda, which is the coupling between the nematic and the optical phonons. So this is the nematic Ising degree of freedom, and this is the phonon. And this big omega here with tau x gives non-trivial dynamics to the nematic variable, some tunneling, which we take to be 5% of this optical frequency omega 0. And interestingly, as shown by also this work, there is a transformation that exact diagonalizes this Hamiltonian. It's not so obvious that this exists because you have the harmonic oscillators coupled to basically a spin half. So U and P, I'm not going to go through all the details. It's some functions G and F times this U tilde and P tilde. So U tilde and P tilde are harmonic oscillator operators, so just these harmonic oscillators. And this F and G, they can be found exactly, analytically, but I just expanded to give a flavor of what's going on. So these functions have some information about the nematic variable. Not by the group that wrote down the solution. They could not find in anywhere. Yeah, you'll have to see what is the coupling here. This is the essential ingredient. But in principle, I mean, it's not so unlikely if the coupling is similar to this. If the coupling is UX times UI, for example, you can as well. What is the effective model then? So we can think of this nematic degree of freedom in an effective magnetic field. So this magnetic field is pointing in some particular direction in the XZ plane, but this direction is given by the occupation of this harmonic oscillator. So if the two harmonic oscillators are in their ground state, the field points along the X direction. Otherwise, it starts to point more and more along the Z direction. So we can think of this effective model as a nematic pseudospin in a magnetic field that depends on the phonon occupation number. And therefore, we can write down immediately all the eigenstates of this model. The eigenstates are of this following form. So we write down the occupations of the harmonic oscillators, and the nematic variable now quantized along a particular direction in this XZ plane. And these are the occupations of the two harmonic oscillators, the X and Y harmonic oscillators. And this doesn't work when they are equal. When they are equal, it's something, yeah, this is an expansion, but we know the exact function as well. Okay, so this is the model for a liquid. So this is what was proposed for a liquid, and this is the full spectrum. So you have the levels, and then if you put some interactions, these levels starts to split, the up and down variables split up. So for the glass, we freeze these Ising variables, and if we do that, it becomes trivial to solve. We have two-dimensional harmonic oscillators that are decoupled with different frequencies now along X and Y, but they are completely harmonic. So this is, I'm showing the spectrum for changing the quantum number of the X, the HX oscillator. I will not spend much time by analyzing the solution. It's the standard harmonic oscillator transformation for X and Y. The eigenstates are also of the 2D harmonic oscillator, and these are their energies. And to model this glass phase, we are going to consider the average over the possibilities of this nematic variable being +1 or -1 on different sites. And we're going to say that on average, half of them are +1 and half of them are -1. This is what we mean by glass phase. All right, so let's try to contrast this glass phase with the liquid phase. And for that, the first thing that we can always do is to look at the linear spectroscopy, linear Raman spectroscopy in this case, and we are going to analyze the responses of the polarizability. So the polarizability can be expanded, I'm calling it alpha, in terms of these U's. So there's a linear term and a quadratic term, and so on and so forth. So first, let's look at this chi, which is just a linear response. It's the commutator of two U's. It's the simplest thing that we can get. And for that, I'm going to introduce a technique that has been very useful for us to look at different correlated systems. That is called the Liouville quantum pathways. So for linear response, this is not necessary, but as we go to nonlinear responses, the calculations become basically gigantic, so it's much better to have a proper way of organizing them. So here we represent time as moving along the y direction, and here are the pulses. And we start with the density matrix that is the ground state, basically. That is where we are computing this expectation value. So at this temperature regime, we can consider the oscillators at their ground state and just worry about the dynamics of this nematic variable that I'm calling sigma here. And then this density matrix interacts with a pulse. I'm representing the interactions by these dots. So if it's a UX interaction, it changes this quantum number by 1, and then it changes it again to 0. It's important that this final state here has to be a diagonal state as well. And there are rules that we can write down to what are the Liouville quantum pathways that we have to compute for any arbitrary response. But I would like to point out that it's very essential here that we actually know exactly the eigenstates. So this is, in a sense, a Raman representation that I'm using here. It's not often that we have the luxury of knowing the eigenstates. We do for this model, and we also do for the Kitaev model that we studied recently. As usual, we want to look at the response functions in frequency domain. So we just Fourier transform. The energy differences that we're going to measure are always going to be the different energies between these intermediate states here. For example, in this case, the 1, 0, minus 0, 0. And we also give a broadening gamma to these levels that I'm not showing here, okay? Once we know the Liouville quantum pathways, we can easily convert to linear and nonlinear responses. So here I'm just showing the linear response with the G function, so it peaks when this energy difference is omega, and the matrix elements that we can read out also from this pathway. But let me represent this as a plot. It's much easier to understand what's going on. So if we plot the chi-xx as a function of omega, when there is no coupling or a very small coupling between the easing degree of freedom and the phonons, it's a single peak. But as we increase lambda, these peaks start to split up. This is the dynamical splitting that I was mentioning before. But notice if we compare this, let's say lambda equals half. If we compare the liquid with the glass phase, it's rather similar. The two positions of the peaks are almost identical, but the amplitudes are slightly different. So linear response is not the best way to distinguish one possibility. The glass is just the numeric degree of freedom freezes, but on average it freezes, it has zero average, so it's a local object. So in half of the sites it freezes up, and half of the sites it freezes down. Yeah, we are not adding additional terms that could lead to that. This is the simplified. Yeah, you can. Well, by looking here, you write side by side this Hamiltonian, and you can just condense these variables on different sites. This nematic degree of freedom can locally condense on different sites. But these sites are disconnected. Uh-huh. That's right. That's right. That's right. And well, yes, that's precisely true. Okay, so let's now look at nonlinear Raman spectroscopy to see if we can get a more clear information about, or a more clear distinction between the liquid and the glass phases. And this has been measured, proposed and measured in some works in the 90s. So these functions have some names, R3, R5, and R7. So the R3 is what I just described. It's a linear response we just insert 2 times the polarizability. And then we are going to look at the first and second nonlinear responses that I'm here calling R5 and R7 with these nested commutators here. So let's see if we can get a more clear distinction between the nematic, what I'm calling nematic liquid and nematic glass. And just to point out that even experimentally, this has been measured before for some molecules. This was done in the late 90s. I'm showing here some response as function of 2 frequencies, and it's going to be very similar to what we are going to compute for this model as well. Okay, so let's first look at the first nonlinear Raman response, in which we have these 3 insertions of the polarizability. The pulses are represented here. So if we just replace this alpha and replace with linear order in U, this is 0. This is 0 for both the liquid and the glass phases. This, by inversion symmetry, this response vanishes. So we go 1 order up, and we expand in quadratic order in U. So we are going to use this term here. And there are 3 possibilities of where to put the U squared term. We can either put it here, or here, or here. And of course, the final response will be the sum of the 3, okay? So let's look at first case in which we insert the U squared term here at time 0. Okay, we can draw the pathways. I'm not going to show all the rules. There are some, we have to sum over the intermediate states. Here the intermediate states are labeled by this M, and the M can be 2, 0 or 0, 0 for this particular case. I'm using everything to be along the measure, the interactions to be with UX here, okay? And just looking at these two pathways, we see that if the spectrum is harmonic, the energy difference between the 1, 0 and the 2, 1 is the same. So these two pathways cancel exactly. So for a glass phase, we have no signal. This contribution completely vanishes. While for the liquid phase, we still have distinct peaks. So this shows a very clear difference in nonlinear response between the liquid phase, which has a finite response for this, and the glass phase, which doesn't. Oh, sorry. Now, of course, this is just one term. We have to put all the possible insertions here, and I'm representing the quadratic interaction with the pulse by the red dot. So the red dot can either be here, or be here. And end of the day, we have to sum all of this to see if we get anything different. It's not enough to just look at this first plots here and say, well, the glass doesn't have anything the liquid does, because this is going to be added up with this contribution and this contribution. So the question is if the distinction still remains visible after we sum over all of them. So let's do that, and the answer is yes. There are very pronounced peaks that are present in the liquid phase. I'm zooming in for this peak here, for example, and this is completely absent in the glass phase. So end of the day, we compute these responses, we get a vast collection of peaks, and then we just look at some particular pathways and try to identify what is possible for one scenario that is not possible for the other scenario, and then we select a peak that could be in principle present for one and not for the other, and see if this peak survives when we add up all the terms. And in this particular case, it does. All right, so from this response alone, we already see that the nonlinear response of the liquid shows peaks not present in the glass phase. So this peak, for example. So it's a clear distinction in nonlinear response between the two possible phases. And this comes from the harmonic versus anharmonic spectrum. Recall that this glass phase, since the Ising variables freeze at arbitrary direction in different sites, the spectrum is still harmonic. But it also shows the dynamics of the nematic degree of freedom. So even if we add a bit of anharmonic terms here, we would never get a peak like this. This peak comes only from the dynamics of this Ising variable. This is what I wanted to show about the first nonlinear response. And it already captures basically everything, but we can also look at this other response R7. So that involves 4 different commutators of alpha. And here we can keep linear order terms in U only. This is already possibly finite, so U. We don't have to put the U squared insertions, so that's an advantage of this response. And now what happens is that the Liouville quantum pathways start to proliferate. So now we have many pathways. We have a total of 8, but we can reduce this to 4 by using time reversal, and we have to just sum over intermediate states. It can be a bit boring to do, but it's definitely doable. And for the glass phase, this all add up to 0. And this is a consequence of having a harmonic spectrum. If you put a bit of harmonicity, this doesn't add to 0 anymore. But again, the peak positions are clearly very different as compared to the glass phase. So here we could, in principle, have 3 independent frequencies that are associated with T1, T2, and T3. But we're going to set T2 to 0. That is equivalent to integrating over omega 2. And we are going to just look at the omega 1, omega 3 plane. And for this, we're going to look at how the level broadening changes what we see in the liquid phase. So if we start with very small broadening, or the broadening is small compared to this big omega that gives the non-trivial dynamics to the Ising variable, the tunneling dynamics, we can clearly see all these distinct peaks in nonlinear response. These are separated roughly by big omega. But as we start to increase gamma, or the levels start to become more broad, these peaks collapse. They don't cancel exactly, but they start to decrease in amplitude until a point in which you don't see anything. So this R7 can also be a probe of how large these values of gamma are compared to these values of omega. So these peaks here show the dynamics of the nematic. I'm basically done. These peaks show the dynamics of the nematic liquid. So at that point, at this point, I hope that I convinced you that nonlinear response can be a powerful probe of quantum materials. I briefly mentioned this work on Kitaev model that can tell us the difference between the Z2 gauge fluxes and the Majorana matter excitations by using nonlinear spectroscopy, and also some work that we are recently we're trying to finish on distinguishing a glass phase from a liquid phase and the different signatures that are present coming from the harmonicity of the spectrum, and we're contrasting also the coherency of the nematic degree of freedom that is lost in the glass phase, but it's present in the liquid phase. So for future direction and work in progress, we are also exploring other strongly correlated systems using similar ideas. But again, for this Liouville quantum pathway approach that I described, it's important to have at least some approximation to the spectrum, which is possible in these two problems. But we are also studying superconductivity and other correlated phases in which all of this can be done solely in terms of Green's functions. So that we can also write everything down in terms of Green's functions. Okay, with that, I would like to thank you for your attention, and I'm open to questions.
Thank you, Vitor.
This is really fascinating and interesting, but I have a specific question. In the old days, people studied fluctuators in systems like spin glasses. You can imagine spins are flipping, and then you can couple it to inducer dynamics. For example, the collection electrons can scatter. And you can measure noise spectroscopy. So in other words, you can measure the time-dependent response. And by measuring various correlation functions of that noise, you can determine whether the fluctuators are actually being frozen, or they start interacting strongly, or they're independent, right?
Okay.
So this is very similar to this. But this is a concept that in principle could be, you could imagine that this is actually happening also in the classical domain. You can have harmonic oscillators coupled to a classical Ising system, and then you give it Langevin dynamics. Now, because the two-level system is classically also nonlinear, the classical dynamics that you could get from this also has some spectral properties in the nonlinear, or in other words, high-order correlations will be different if the two-level system has dynamics, or trivial dynamics, or some correlated dynamics, or it's frozen, right?
Right.
So why is this restricted to the quantum domain? This is what I don't understand. You could put Langevin dynamics. So my understanding is that you supplement the two-level system with some dynamics.
Yes.
And then you have envisioned two different types of dynamics. And then that influences the harmonic oscillators, and you couple this to external field, to optics to probe this, right?
Right.
You could do this if you also have a classical Langevin dynamics of everything, right?
Right.
Why cannot it be repeated in the classical domain, or everything you've done?
I would have to think more about it, but maybe it can. I mean, this problem came to our attention in this particular context.
So this was called, doing higher order correlation. That was called the second spectrum analysis, which was put forward by Mice Weisman. And Dragan did a lot of experiments on electronic system doing this, in fact.
Okay, I would be very interested in discussing this in more detail. So again, this came to our attention with this particular question, if this could be distinguished between, if we could distinguish these two possibilities. So it was, just to give some context, this was measured first, and then it was proposed that this Ising variable is not frozen, therefore you have this peak splitting that happens before a transition in which it would be frozen. So, but then we had to contrast this with other possibilities, and that's what we did. But I would be very interested in discussing the history and other works related to this.
Victor, very nice stuff. There's a third scenario besides the liquid and glass, which maybe, it is more trivial. It's the tau Z couples to B1G strain, the tau X couples to B2G strain. Yeah. So if you have random strain, even though their averages are zero, because they're in quadrature, you're going to get a finite splitting.
Right.
Would that add another case that you would have to distinguish, or there's an easier way to rule this out?
Yeah, we Yes. We analyzed strain a little bit. We found out that for most scenarios, I'm not sure if we addressed this particular scenario that you're asking, actually, but for most scenarios, linear response would be sufficient to distinguish. So we are just trying to see possibilities that are in which we would have to go beyond.
I have a question that is maybe related to what Raphael was asking. So is it particularly useful, this method, for this problem, because there are actually two time scales that live on very separate scales, right? You have the oscillator frequencies, and then you have your cap omega, which is how was it, factor 20 suppressed or something like that. So is it the right way of thinking about this as saying that if you have more than one pulse, right, that you can actually pick up on these directly on these two different time scales? Is this the right way of thinking about that?
It is, yes.
Because during that, again, it's a naive picture, during that gap between the two pulses, right? In one case, your taus change, and the other, they don't.
That's precisely true. That is what is giving.
But if that's the case, right, that would answer your question, right? Because in that static strain scenario, this would not happen. Thanks.
Short question, last one.
I have a naive picture of the glass being very, very, very slow dynamics.
Yes.
Slower than your measurement timescale. So in principle, a liquid will behave like a glass if your measurement timescale is much shorter.
Right.
So I'm just wondering, in your simulation, is it possible to change the parameter of your liquid phase such that you can start to approach a glassy behavior, and you can smoothly see how the glass behavior emerge?
Yeah, that'll be the dream. In our in our glass here, we are just freezing and not giving any time scale to that. So, but sure, this is something that we plan to do in the future, to see how one limit interpolates to the other limit. But we are not quite there yet.
Okay, let's thank Vitor again. So we have words from Eduardo's advisor.